think it's 10 a.m. Dr. Aisha, should we start? And welcome again to this forum and the second technical session after an exciting and enlightening session, the opening session, which I think introduced very well the different challenges and the future perspectives of the energy sector, and specifically the renewable and clean energy sector. And if there were two issues that were, I think, at least attracted my attention as an expert in signal processing, is the concept of efficiency and lowering emission. I think these are the two words that I felt that the industry is looking at working on, and looks at contributions from the academia in this, in basically finding solutions for such challenges. And we are really fortunate that throughout the day, we have experts from different areas, from the Far East to the Far West, who are leaders in this field and who will share with us their views, their experience, their work, their findings, and the future of this sector over the next few years. For this first session, we are very fortunate to have three experts in the field. Professor Martin Green from University of New South Wales, Professor Akhtar Kalam from Victoria University in Australia, and Professor Fausto Pedro from Spain, University of Castilla-La Mancha. So we will give around 45 minutes or so, actually about 35 minutes or so for the presentation. Then we'll open the floor for some questions. Please feel free to write your questions on the Q&A panel, and we will hopefully will have a time to offer an opportunity for those who want to ask their questions verbally. So the first presentation is going to be given by Professor Martin Green from University of New South Wales. And the title of the presentation is How Cheap Can Solar Photovoltaics Become? And I think everybody is looking forward to listen to Martin on this topic. Professor Martin has a very long biography with a number of years of major achievements. I will just mention a few of them. Then I will give the opportunity for Martin to speak. So Professor Martin Green is a Scientia Professor at the University of New South Wales, and he's the director of the Australian Centre for Advanced Photovoltaics, which involves a number of Australian universities. His contributions are major, but mainly in photovoltaics, which include inventing the PERC cell, which is a well-known commercial product, and holds the record for silicon cell efficiency for about 30 years over the last 37 years. He has received a number of awards, including the 1999 Australia Prize and the 2002 Right Livelihood Award, which is kind of an alternative to the Nobel Prize, and holds the 2018 Global Energy Prize, which was presented in Moscow. So it's really indeed a pleasure to have him among us here. So it's late in the afternoon for him, and we thank him for waiting to speak to us in the afternoon. Please join me in welcoming Martin for his presentation. Please, Martin, proceed.
Thank you very much. Just see if I can. I've just got to find out how to get my slides up.
Vrish, could you stop sharing your screen, please?
Unfortunately, oh, here we go. Yep, the screen has changed. There they are. Okay, yes, I'm Martin Green from UNSW Sydney. In the middle of the photo at the bottom there, that's the laboratory building that I work in, and on the far right is the solar industrial research facility where we do technology transfers of the technology that we develop at the university. So very strongly linked to the industry, as you'll see from the talk. But what I'd like to do today is just explore how cheap can solar photovoltaics become. One way of doing that is to look at the history of how prices have reduced historically. And this is a graph that was published a year or so ago. The purple lines are prices and the orange ones are costs. There's not always been a big difference in the photovoltaic area. But for over 20, 25 years, you can see that you can fit this curve by a straight line. It's on a logarithmic axis in terms of the price and just a timeline on the other. So that means exponentially reducing costs. So it's like a generalized Moore's law. So Moore's law says, a number of transistors doubles every year or every 2 years, depending on the time that you're talking about it. But for photovoltaics, the cost for those 25 years decreased by a steady 7% a year, as you can see from that dotted line, that's a bit of a fit. So that was really good. So I can remember not all that long ago looking at curves like this and extrapolating and saying, well, wow, by 2020, at that type of cost reduction, we're going to be at $1 a watt, and we're going to be able to do all kinds of wonderful things once we get to prices that low. But, as you can see from that curve, something much more dramatic has happened. And we're already at costs of photovoltaics below 20 cents a watt, so 5 times cheaper than where everyone thought we'd be. So obviously something quite dramatic has happened, and I'd just like to go over that because we were quite heavily involved with this, so I can give you a bit of an insider's perspective on how that all occurred. So the key to it all was this gentleman shown here, who is Dr. Zhengrong Shi, who was my 12th PhD student. So he finished his PhD with us and was working with us on commercializing some of the technology we were trying to get into production. But he got inspired by the desire to go back to China and set up a manufacturing line there. This was the late 1990s, and China had just opened up new opportunities for private companies and things, and he was keen to go back there and take advantage of the new business climate that was developing there. So he was very successful. So with help from people from our team, he set up a manufacturing line and got into production, started selling solar cells internationally, and sort of opened the floodgates for the whole industry. This is just indicating the floodgates there. But what he did was his progress was noticed by some US investment banks, namely Morgan Stanley and Goldman Sachs. So they approached him and organized a management buyout of a very small company that he was operating in that was mainly being supported by rather reluctant Chinese shareholders who had had their arms twisted to help finance this endeavor that no one thought was going to go very well. But he listed on the New York Stock Exchange in 2005. So it was quite a notable listing in that it was the first private Chinese company to list on the New York Stock Exchange. And it's also reported to be the largest technology float of 2005. So suddenly this very small company got transformed into $1 billion company through the fundraising. And Zhengrong overnight was catapulted to becoming the first solar billionaire. So he became very famous as a consequence. I was fortunate enough to be up there on the stage ringing the bell along with another person from our lab, Stuart Wenham. So 3 of our lab members up there. But that was a huge success, not only for Zhengrong, but for Goldman Sachs and Morgan Stanley, who made hundreds of millions of dollars on the listing. So that encouraged mutual interest between Chinese companies wishing to repeat what Zhengrong had done, and US investment banks wanting to shepherd some more Chinese companies through the listing procedure on the US exchanges. So there was as soon as other companies could get themselves organized, it took about a year or so before the next one listed, but there was a spate of listings on the US exchanges. And because Zhengrong was from our lab, the grooming of these companies for listing required they have some contact with a reputable laboratory. So many of my students or former students got snapped up and became CTOs and so on of these endeavors. So I've got some of them circled there. There's some of the next listings. But what happened was there was 9 Chinese companies that listed on the New York Stock Exchange between, well, not the New York, but US Stock Exchange between, I guess, 2005 and the global financial crisis in 2008. So these companies got through the floodgates then, and if you're the ones that are marked in red, they remain in the top 10 of manufacturers last year. So, you know, the backbone of the industry is formed by these companies that got a boost from the capital injection from listing on the US exchanges. Most of them, 9 of the 10, had people from our labs as founders or CTOs, chief technical officers or chief operating officers or so on. So very well connected to the industry as a result of that. Go back to this slide, and on the right is a chart just showing the capital raising. So the first one was the end of 2005. That was Suntech, Zhengrong's company. It raised 400 million. And then after that, the floodgates opened, and a year later, the next companies listed and many more. And through listings and debenture note issues, there was over 7 billion raised very quickly from these listings and associated activity. So this injected a huge amount of capital into the industry that was spent up in building up production lines, and created intense competition between these highly cashed up companies. So that forced the prices to dive downwards as these companies sort of struggled for survival as they competed against each other, all with the best equipment and so on because of the money they'd raised through the US listings. So that was responsible for that first big dip there. So rather than the steady 7% a year that I spoke about, there was a overnight sort of dramatic reduction in the cost of panels as these companies competed against each other. And if that wasn't enough, some of the state-owned companies, these were all small private companies, you know, generally, you know, what I'd call tin pot companies, suddenly becoming sort of billion-dollar companies through the capital raised through these listings. But state-owned companies in China have plenty of access to capital, so they didn't need to list. They just invested their own capital into trying to outdo these private companies. They were quite confident they'd drive them out of the industry. So there was a second round of very aggressive competition between these companies, between the state-owned companies and the private ones, which the private ones won. Most of the state-owned ones were driven out of the industry after huge losses. So that's responsible for that second dive. And very quickly, rather than having to wait to 2020 to get below $1 a watt, in 2012, the average selling price, wholesale selling price of solar modules dropped below $1 a watt. So these figures that I'm showing here are what are called the average selling price that a number of market survey companies document. So since then, we've been in a more steady progression. But again, it's these large companies, now large companies, competing against each other, mainly based in China, that is driving down costs. So if we now look at the generalized Moore's law, plotting the log of the cost versus, or in this case, the log of the price versus the timeline, we see we're again in an exponential region, but with a much more aggressive price reduction. We're now in a 20 to 26% sort of cost reduction per year. So that means the price is halving every 3 years. So this is the photovoltaic form of the Moore's law. So over the past, 6 years or so, we've been in this period where we've been having a halving of price every 3 years. And I'm pretty confident we're going to have at least another cycle of that. So over the next 3 years, we're going to see the prices halve again. Not sure what's going to happen after that, but it's already been following that pattern for quite some time. Just while I'm on this slide, I'll just note that the average selling price, so these prices are reported by these companies, in this case PV Insights, are backed up by auctions within China. So there's often these large auctions of modules where large amounts are purchased en masse, and those prices sort of provide some backing for these market survey figures. But for a modern module, modern modules have sold this year for 17 cents a watt. And the efficiency has been going up. Our chairman mentioned efficiency, but that's been going up. So modules are now 20% efficient, which means they give a rating of 200 watts a square meter. So you multiply those two together, you get the selling price of modules is now about $34 a square meter. So you think about other things like carpet and tiles and all that kind of thing. There's not too many of those you can buy for $34 a square meter. So solar is becoming very, very cheap. And as I'll tend to indicate, becoming even cheaper. So another way of trying to estimate how low they might become is through these learning curves. They've been very popular in photovoltaics. So they'll develop, well, first used for costing of, I think it was airplane manufacturer in the 1930s by a guy called Wright. So this is Wright's law. But the very first one I saw published in Photovoltaics was in 1972 by Martin Wolf. And most of the data on this curve was from making cells for spacecraft, which was the only market until the late 70s. But if you just took his learning curve, and I went through this exercise earlier this year, but just extrapolate until the end of 2019, you get 3 something or other cents per watt at 631 gigawatts, which is the total amount of photovoltaics that had been produced up till then. So if you just had believed Martin when he published this curve way back 40 something years ago, you would have predicted that price, and then converting it to dollars of the day, you get to 21 cents a watt, which is just about exactly the price that photovoltaics was selling for, at least wholesale, at the end of the year, at the end of 2019. So it shows the power of this method. If you had confidence in that approach, you could have foreseen the future. There's a little bit more subtlety to it in that this is a similar exercise that was done by CITI Research in 2000, using data up to 2011, and they were trying to estimate prices for 2020. So just taking the learning curve, this is the showing the type of thing on the simpler graph earlier, just showing the selling price of photovoltaic modules along this axis, log of it, against the log of the accumulated volume, the amount that's been sold. So just extrapolating it to where we're expected to be in 2020, just fitting a straight line to this, you get about 53 cents per watt. But if you're a little bit more subtle in your interpretation of the learning curve and recognize that there's actually a couple of different divisions here, rapid initial learning. This is called industry maturation phase, where things like supply chains were ironed out and so on, where you got slower learning rate, and then full commercialization phase where you go back to a high learning rate. In fact, the learning rate now over recent years has been 40%. So extrapolating from 2011 at this 40% learning rate gives you something like 25 cents a watt, which is fairly close to where we actually were at the end of, well, we actually are now in 2020. So the industry is learning very quickly. So 40% rate means the price halves every 2 years. So we've seen the, so that's very similar to the figure that I quoted before. So both of those were top-down approaches, just looking at broad figures and then trying to work out from them what might happen in the future. I've just lost my timer here. I'll have to go without it. If you go the opposite approach and just look at what might be the lowest you could make a module for, if you just looked at the materials that go into the module. So, discounting the cells themselves and just look at the other more maintained materials like glass and aluminium and so on. So the cells are encapsulated under glass. There's an aluminium frame, And there's polymeric encapsulation layers that bind everything together and provide a backing sheet for the module. So if you just look at the cost of those, this year, this costing was done by NREL. They found out there was about $17 worth of these materials within a module per square meter. So that's about half the cost of that $34 a square meter that I mentioned before. So you might say, well, there's your answer. If these more stable materials that less reduction for cost, less potential for cost reduction with, are going to peg you at 17, you might go down to halve, and that's going to be it. But the really interesting thing is, if you plot the way the cost of these more stable materials have been varying, and NREL periodically does these cost studies so that they compile the data on these for these studies, but this is just using the data they compiled at different points in time. You find that these stable materials are reducing quite strongly in costs as well. So not quite 20%, but somewhere between 16 and 18% for the major material components. So the bottom-up approach doesn't really give you an answer, because as the industry increases, once the glass used to be supplied by, running a glass factory for a couple of months a year on producing solar glass, and now there's dedicated float glass factories being built to build it. So there's all these kinds of economies of scale that are getting introduced, that is also driving down the costs of these basic commodities. So this type of learning, this type of cost reduction here, we're back to Moore's law type of behavior here, that corresponds to cost reducing, halving every 4 years or so. So not quite as fast as the overall module costs, because the cell costs are coming down more quickly than this. So end of all this, I haven't got a firm answer for how low you might go. From the top-down approach, you can go as low as you want to, just extrapolating trends that are showing no signs of saturating. And from the bottom up, you might think you can run into firm costs by looking at some of the basic components used in the module, but some of them might not be essential within the module, and anyhow, the cost of those are decreasing quite rapidly through economies of scales and larger ordering, larger bulk orders and all this kind of thing. So my first conclusion, how cost can photovoltaics become? And I like this descriptor by Ramez Naam, made recently, insanely cheap. We're going to have very cheap solar. So already in many parts of the world, and I imagine this is the case in Saudi Arabia, it certainly is in Australia, photovoltaics now provides the cheapest form of electricity generation, and it's going in at a very rapid rate in Australia as a consequence. But it's going to be a lot cheaper. So even though it's already eclipsed any other form of electricity generation now, it's going to be very much cheaper in the future. So some of these issues due to storage and so on, I think are going to disappear, because you can just keep installing more photovoltaics to reduce the amount of storage you're going to need, because the costs are going to be virtually nothing. So I already said the photovoltaic modules are halving every 3 years, and I expect that to go on over the next 3 years. So I expect us to get down to 10 cents a watt by sometime in 2023. But the question you might ask is, can this keep going? This exponential reduction with time is sort of a generalized Moore's law, as I mentioned before. If you look at Moore's law, originally it was number of transistors on a chip doubling every 1 year, and then in 75 Moore broadened it out to doubling every 2 years. So this chart shows the dotted line shows doubling every 2 years. So up to the end of last year, it looks like the industry was continuing to follow Moore's law, even though there's the same sort of physical constraints on the number of transistors you can squeeze onto a chip. I guess eventually the size of an atom, quantum computing was mentioned in the discussion at the end of the last session. So eventually the size of an atom. Again, showing no signs of abatement. So maybe photovoltaics can continue for a few more cycles. The technology that our group developed in the 1980s that is doing very well was the PERC cell. It stands for passivated emitter and rear cell. The emitter is just the top and the rear is the rear. So it's just fixing up the top and the back of the cell. And that cell structure down the bottom is one that I personally invented in 1983. And then the team that you can see there actually developed and made it work and got it to world record efficiency levels during the 1980s. Took it on to 25% efficiency, which for a long time, for many years, was the world record for solar conversion efficiency. But now the technology is starting to have market impact. So as was mentioned, efficiency is a key driver for lower costs, particularly in a technology like this, where you've got things like the glass and aluminum frame, where the costs aren't reducing as quickly as the cells. If you can increase the efficiency, you can effectively reduce those costs more quickly by reducing the amount of material you need for a given wattage rating. So the chart on the right there just shows how the PERC technology has rapidly overtaken the market. So the dark blue region shows the previous incumbent, which was the dominant technology for 40 odd years. But the light gray and yellow regions and some of the black shows the uptake of PERC technology. So since 2015, it's just completely obliterated all comers and taken over the whole industry. So this year, about 86% of the production will be PERC cells. And that's having a big impact in driving the costs down further, as I'll explain. It's doing that through introducing increased functionality. So one thing that's easy to do with the PERC cell is to make it respond to light from both directions. So you might wonder, if you're not involved in photovoltaics, what's the use of that? The light comes from one side, but there's a lot of light scattered onto the rear of a module. So if you set things up correctly, you can get somewhere between, well, you can get 5% at least, even if you don't set things up correctly, and 20% if you do a good job of encouraging light to fall on the rear of the module. So this is a photo from Longi Solar, one of the top 10 manufacturers. But if you put full sunlight on the front of the module, you'll get 455 watts. If you put full sunshine on the back, you get 342 watts. So nearly as efficient from the back as from the front. So not quite as efficient. But it turns out that making these cells respond to light from both directions doesn't cost any more. It might even save you costs because you don't have to pay for the metal that would normally cover the rear. So that's one thing that's having a big impact on costs, because you can get this 5 to 20% increased energy generation by the module, and that comes straight off your bottom line. The other thing that it's easy to do with these cells is to cut them into bits, and that's encouraged people to make smaller cells. So the solar cell can produce enormous currents. So it's 400 amps a square meter that a silicon solar cell can produce. So you don't want a solar cell that's a square meter, because handling 400 amps would require very thick copper conductors. So you want to cut the cell into a small area, so the amount of current that you have to handle is reduced, and that reduces the cost of connecting the panels and everything together, get the voltage up high as quickly as you can. And so companies are now using half cells. So traditionally the panels used a whole cell, and the cells were sort of squarish in appearance, whereas now they're very rectangular in appearance as you chop in half. That solar car there was the first use of half-cut PERC solar cells, and that they were made by a team from our lab for the solar car race across Australia, and that's the Honda car that blitzed the field and set the race record using these half-cut PERC cells. But the whole industry is following that route. And instead of having the cells neatly spaced apart with white regions between them that are largely wasted, a technique that we use there called shingling, or developments of it that have the same effect, are being used commercially. So tiling and shingling are being used commercially as a result of the introduction of PERC. There was none of it done before PERC was introduced commercially. So all the manufacturers have their own tiling approach. Longi and Jinko are two of the big manufacturers, and the whole module is being tidied up so you don't waste any area, as you can see there. So all this has come about since PERC's being introduced. It sort of opened the floodgates of creativity within the industry. So you've got bifaciality, half-cut cells, tiling, shingling, all coming into the market together, all acting to reduce the cost of the modules, as well as the improved efficiency of the PERC, which was the initial reason for introducing it. So now you can cut cells into a half. It's changed the way people think about the size of the wafers that you can use in manufacturing. So for a long time, the industry was stuck with these 156 millimeter square wafers. That's 6 inches for people that work in imperial units, but they were introduced into manufacturing in 2012. So one of those cells that you can see there will generate about 10 amps. So that's, you know, that's an amount of current that's getting on the limit of what you can conveniently handle without going to very thick copper conductors. So that was providing a bit of a barrier to the industry going to anything bigger. But people, once they realized they could start cutting into a half and smaller, suddenly you got interested in bigger and bigger wafers. So now the industry is looking at 182 and 210. There's a battle between different manufacturing groups between those two wafer sizes. So this just gives you a better idea of the difference between a 210 millimeter wafer and a 156 one. So, you know, quite a substantial difference in area. And since that's the unit of production is one of those wafers, you know, that means all your production costs can reduce, you know, not quite proportionately, but you get some fraction of that proportional reduction in your manufacturing costs of the cells as a result of that. So you can see why I'm getting confident about this, another cycle of 3-year halving in the cost reduction. The Chinese have got quite excited by these big wafers. So the company that introduced them to the market, called them the Kuafu wafer. So Kuafu, who was a legendary Chinese character or giant who tried to tame the sun. So a very appropriate name for these big wafers. They're certainly going to do that through introducing cheaper photovoltaics. So if you look at what's happening in the industry, the whole industry is very quickly switching to these bigger wafers, which you can cut into halves or thirds is the two options. So this just shows new capacity. So if you look to the far right, you'll see the 182 and 210 columns. That's the, and underneath them, they're the figures of representing the amount of new capacity going in for those two sizes. So some legacy capacity going in with the smaller sizes, but mostly addressing the big wafer sizes. So we're going to see cost reduction from that. So if you compare us to the microelectronics industry, the yellow circles show the size of wafers used in microelectronics. So there's a steady progression up to the early part of the century, going up in different inch sizes, up to 12 inch or 300 millimeter diameter at the turn of the century. And photovoltaics sort of lagged behind. But all of a sudden with these 210 millimeter wafers, that's the largest you can cut a square wafer out of a round 300 millimeter ingot. So we caught up to microelectronics. So this was a diagram that was released about the time that the 300 millimeter wafers was introduced into microelectronics. So it's a slide from about 2001. But it took about 10 years to go from 200 millimeters to 300, 50% improvement. And the microelectronics likes these 50% jumps. So the next size target was 450. So the thinking was, you know, maybe by 2012 we'd have that. And by now we'd be having the next 50% increment, we'd be up to 675 millimeter wafers. But the microelectronics industry has stayed with 300 millimeters because mainly because I think the challenges in lithography, getting these nanoscale dimensions over bigger and bigger areas poses enormous challenges for the equipment that has to do that, and enormous expenses in building and buying that equipment that can handle these larger wafer sizes. So the industry has stayed with 300, and the present timeline for 450 is 2029. But I'm just thinking with all this, you know, for photovoltaics, handling the big wafers in production would not be nearly as demanding. So you don't have to do any of this fine line lithography or anything within solar production. So I'm just wondering if all this big interest in bigness within the photovoltaic industry might mean that we leapfrog microelectronics and get ahead of them in terms of wafer size. Certainly, we're going bigger with modules. So this just shows evolution in module size. So some of the modules now are well over 2 square meters in area, and some even 3 square meters are certainly on the drawing board, if not already in production. So becoming bigger very quickly. So that guy in the middle there is drawn to scale. The biggest module that's actually, I think, been shown anywhere is a 800 watt module that was exhibited at the recent SNEC conference in Shanghai. So that's the largest that's been built. The main issue with making them bigger is they're normally carried by 2 people. So if you get them over 40 kilos, that becomes a little bit more challenging. So people have been trying to keep the weight under 40 kilos. So this particular one here is a 550 watt module from the company Trina. It weighs about 27 kilos, if I remember correctly. So, can be comfortably handled by 2 people. About a decade ago, one company introduced solar cells based on a different, less efficient technology, an amorphous form of silicon. And they went for very much bigger modules. So they were 6 square meters, so double the bigger size that's being talked about now. And they were very heavy. They weighed close to 100 kilograms, so too heavy for 2 people to lift comfortably. So the company involved helped develop automated equipment for installing them to encourage market development. So this is a type of thing that you could do with automated equipment. So if you, instead of using amorphous silicon cells, I think these are about 400 watt rating, but if you used PERC cells instead of amorphous silicon cells, these would be about 1.2 kilowatt rating. So you're getting to a substantial power rating. This interest in large size encouraged me to look back at some of the old literature that was done when we had a clean slate back in the 80s about, what was the optimum size of a module. There's plenty of studies of this type that were done then. And I found that one company deduced that 40 foot by 8 foot was a good size, because that was the largest size that you could carry around the countryside on a semi-trailer. So that that would be 30 square meters. So you'd get something like 6 kilowatts out of it with PERC cells. But you just could imagine much more being done in the factory with a large module like this. You could have it all wired up and the AC converter and everything connected into it before you took it to the field, and making field installation very much quicker and smoother. But too heavy for 2 people to carry, so you're certainly going to need automated equipment to install it. Well, just to finish off, I'll just talk about some of the benefits and challenges in going to bigger sizes. So there's been some recent studies that have looked at what type of cost savings you can get by going to these bigger wafers in particular, and the larger modules that result from them. So this particular study by unnamed but well-known local, meaning Chinese, Design Institute, they compared the standard, which is the blue, to 182 millimeter wafers, which is the orange, to 210 millimeter wafers, which is the gray. And they got about a 4% going up to 6.5% cost reduction by going to the bigger wafers, depending on the specifics of the location and so on. So the biggest cost saving in this case was for a lower insolation, higher latitude location up to the north of China. So that was a study involving Chinese installations. International company DNV did a similar study, and they found something similar. In Spain, they found something like a 3.5% lower cost for the 210, and in Texas, 3.6. So, roughly similar figures, slightly lower, but similar to what was found in the Chinese study. So there are cost savings to be made, and I'm sure these will probably grow as the market refines the product and gets more used to handling them and so on. I think we'll see even larger cost savings from that. what might be the challenges? As I said, there's been enormous changes introduced along with PERC over the last 5 years. And so some people worry, like the solar industry has been a very stable industry. It depends upon the durability of the module for its impact. So modules are warranted for 25 or 30 years now, just routinely. So not many commercial products are warranted for that timeline. So that's been an important part of the success of the business. So changing anything is dangerous in an environment like that. So some people worry the changes are happening too quickly. I'm sure there will be a hiccup or two, but that's the type of thing that'll sort itself out in the fullness of time. The other thing is going to these bigger wafers. So I'm not sure how seriously people in the industry are thinking about it, but certainly for microelectronics, some of the challenges of going to larger wafers has been thought about. And the way you grow these silicon ingots is you dip a seed crystal into a molten bath of silicon, and then you reduce the diameter of the seed, and that gets rid of a lot of crystal defects out of the silicon. So you have this very thin neck, called a dash neck, that then supports the big ingot that grows. So it's a very small diameter bit of silicon, which is very strong, but you're tempting fate to go to really large ingots relying on a narrow neck. So looking at this from microelectronics, they developed this way of going to a growth of a larger diameter neck by the technique shown there, and then instead of supporting the ingot by the thin neck, supporting it by this larger diameter neck. So the big ingot on the right is a 440 kilogram, 400 millimeter diameter ingot grown by that technique. So I'm just wondering whether the solar industry will start taking advantage of some of these improvements and quickly get into making bigger ingots. So that brings me to the end of the talk. I hope I've stayed on time, but my timer disappeared halfway through, so I'm playing it by ear. But how cheap can solar photovoltaics become? I'd agree with Ramaz, insanely cheap. So we're going to see at least a halving in price, probably over the next 3 years. And then perhaps there's another halving after that. Not too sure exactly about that, but there's plenty of technology out there that's still to be exploited. All this large, if you go to 40-foot by 8-foot modules, I think that's got to have a big impact on costs. So the introduction of our technology, which we're very proud of, PERC, has accelerated the pace of change. So it's very satisfying to feel part of all that activity. So I think within the next 3 years, we're going to see 10 cents a watt module. So you might remember at the start, I said, we were very excited about the prospects of reaching $1 a watt modules in 2020, because that was going to open all kinds of opportunities. So you can imagine the opportunities that are going to be opened by 10 cents a watt modules. I think it's something that the full impact of such very low cost electricity generators, hasn't been fully evaluated, but I think it's going to lead to a new era of very cheap electricity, particularly during the daytime. In the past, it's been cheap electricity at night, but situation is going to change. We're going to have cheap electricity in the daytime when it's probably more usable. So thanks very much for your attention. It's been a pleasure to give the presentation.
Thanks, Martin. Thanks, Martin, for this very comprehensive overview. The good thing about it is that we can see that there is a light at the end of the tunnel. And what I liked best was your kind of last slide or before it, where you said too many changes. I would have changed it to too many challenges, too many opportunities over the next few years. Thanks again, Martin. We have a few questions for you, if you don't mind. I will just read some of them. The first question is from Dr. Mohammed Antar, saying that I wonder how feasible is recycling of abundant PV cells due to aging. Will it be an aid or an impedance to industry?
Yeah, there's a lot of interest in recycling PV modules, but it's just part of the general ethos. Any new product has to be recycled. So there's been back of the envelope studies done for Australia, for example. So if we generated all our energy, displaced oil, everything, coal, the whole works with solar photovoltaics, the main waste that you generate is glass waste, over 90% of the weight is glass. and the aluminium frames are easy to remove, so they'd be recycled with as a matter of course. But if you just look the amount of glass waste that you generate by powering a whole country like Australia with photovoltaics, you know, all energy, all primary energy, it would add 40% to the present Australian glass waste stream. So, you know, like it's important that all industries be responsible and aim to recycle their waste, but it's not a particularly onerous task for photovoltaics. The amount of waste getting generated, even in the most extreme scenario, is only you know, only a fraction of what we're presently dealing with. So there's other industries, you know, like the coal industry. The amount of coal ash generated in Australia is just enormous. So, you know, 1 year of coal ash would swamp a lifetime of photovoltaic panel waste, for example. So, you know, it's not a big issue, but it's one the industry is looking very serious at because it wants to be responsible. And in some countries like France, all photovoltaic modules have to be recycled. So there's 100% recycling of photovoltaic modules now in France, and schemes getting put into place whereby you pay for that at the time of sale, so that the cost of the recycling is already factored into the product. So it's something that we're definitely going to see is responsible recycling of photovoltaics, but there's not much of value in the module. It's mainly glass and a bit of plastic, and the silicon's not going to be worth much after it's been mangled in a recycling process. There's a bit of silver, but it's very hard to see it being economic to extract it. So it's going to cost to recycle, but no more so than most industrial waste, I guess.
Okay, thanks. Another question is about dust management. What are the technologies or best technologies currently available for managing accumulated dust over surfaces? Any specific chemical techniques, or what do you see in that?
Yes, no, it can be an important issue in some climates. Like in Australia, it's not a big issue. You don't lose much through dust, but in some regions, like I think in Saudi Arabia, it's probably a much bigger problem than in Australia. So there's been a lot of work done on it. So, you know, one line of research is developing machinery that climbs all over the modules and gives them periodic washes. So that's one approach that's being explored. And the other is various coatings on the modules to reduce the tendency of dust to stick. And if it does stick, making it easier to remove if you get a bit of rain or condensation. So one very clever technique that I saw, it involves hydrophobic and hydrophilic surfaces in different areas of the module. So you try to encourage dew to condense at the top of the module, where I guess you have the hydrophilic material. And then once you get a ball of water condensed there, it rolls down the hydrophobic surface of the module, picking up dust on the way along. So there's some very clever thinking like that that people are exploring, that, you know, might be the way things go, and some clever idea like that that proves economical. You know, putting these coatings onto the glass, you know, probably not going to cost all that much once you get into large scale production. So yeah, it's a definite issue, particularly as the diversity of the use of photovoltaics expands. And, you know, I haven't been to Saudi Arabia, but I've been to other countries in the Middle East, and I have noticed that dust accumulation is more severe there than I see in Australia.
Okay, one quick question also about toxicity and basically those who claim that renewable energy is not truly green.
Yeah, it's the silicon solar cells really have no inherent issues. So there are silicon solar cell manufacturers can offer a completely environmentally clean product. But on the market at the moment, one manufacturer makes cadmium telluride modules. And, you know, so the cells in that module are 50% cadmium. So legislation has been modified to allow that product to be sold on the market in just about every country. Some countries may have it banned, but like in Europe, it's allowed, even though it wouldn't be allowable under their restriction on hazardous substance legislation. But when you're competing against modules that are 50% cadmium, when in the silicon modules, the solders have a bit of lead in them. They use lead because it improves the solderability and so on of the product. You can make modules without lead, and some manufacturers do, but because they've got the lead in the panel, the present silicon modules don't have a completely clean bill of health, although the lead is in insoluble form, so it's not going to leach out or anything in a landfill. So the silicon modules are legal to dispose of in landfills because they pass all the leaching tests and so on. So it's not a big problem, and silicon modules in particular can be 100% environmentally benign. But changing, any changes, as I said, brings risk. So changing a lead solder for a different solder brings a risk, and with it a cost to a manufacturer. So most manufacturers have been reluctant to get the lead out of solders because, it's only a small percentage of lead in there. It's not all lead, but because of the risk and the costs that are associated with developing an alternative product. It is feasible, and some manufacturers have shown that it has. And one manufacturer, like I might mention them because good to encourage people to have a cleaner product, like REC is a company, a Norwegian company that's manufacturing in Singapore, but they manufacture a module that's been certified to have a completely clean bill of health environmentally. But a lot of other photovoltaic modules, like there's modules that are based on cadmium telluride, and there's modules that are based on copper, indium, gallium diselenide. So they have a bit of cadmium in them, as well as selenium, which can introduce problems in landfills and so on. So there's not all photovoltaic products are the same, but silicon is 95% of the market, and it's 95% environmentally benign. It's the closest to being 100% environmentally benign of all the competing technologies.
Thanks, Martin. Martin, maybe just one last question. I come from a signal processing point of view, and basically we look at problems always as constraint optimization problems. Now, from what you mentioned several directions. You mentioned the issue of how big is the cell, the efficiency issue, the material issue, the cost issue, and so on. I mean, what do you see as a quick win?
As a
quick win?
Quick win. Well, it's probably no really quick win. So improving the efficiency, as I think you mentioned at the start, is really very important. And that's what the PERC cell is doing. And the commercial PERC cells now are up, getting close to 23% in efficiency, but in the laboratory we got to 25. So we think the industry will incrementally improve the technology to 25, and that introduces costs all along the way as you do that. The thing that I would like to see most happen is to find a cell that you can stack onto silicon, because if you can stack a cell onto silicon that has a different response threshold to light, responds to light of higher energy than silicon responds to a very broad range from low energy to high energy. But if you can put a cell that's designed for high energy light conversion, high energy photon conversion on top of silicon, you can improve the efficiency, having two cells stacked on top of each other to specialize for the different wavelengths. And you can carry that idea through to 4, 6, 8, 20 cells stacked on top of each other, and you get efficiency gain all the way along. So the problem has been in finding a material that's suitable for stacking onto silicon, because silicon is very durable, reliable, environmentally benign, and so on. And just about any other technology has trouble meeting all those criteria. So I think later on today, we're going to hear about perovskites. And that's probably the most promising material, in that in the laboratory, you can produce very good cells by stacking perovskites onto silicon. But the main issue there that I see is stability. It's like silicon is one of the stablest photovoltaic materials that has demonstrated efficiency over 20%, whereas perovskite is probably the least stable of the 6 or 7 materials that have demonstrated that high efficiency. So it's like not a match made in heaven because of the different stability levels. But people are working very hard on perovskites, as you'll hear. And there is, you know, I'm getting increasingly pessimistic about the prospects, but many people are remaining optimistic about the prospects of developing stable perovskites that you'll be able to stack onto silicon. But in our group, we're also looking at other materials because just in case the perovskites don't win through.
Thanks, Martin.
I should also mention that the perovskites are 30% lead. So if we get the lead out of the solder of the silicon, we'll be putting it back in if we put the perovskites on silicon. So there's a bit of a catch-22 there as well. So we're trying to find materials that are both efficient, stable, abundant, and non-toxic. So that's our criteria that we're looking for, but very difficult in finding something that can match silicon and all those criteria.
That's the beauty of having a game where we have two major players from around the world, yourself, Nasiruddin, and the others as well. So it's great to have all of you here. Thanks again, Martin. It was really a pleasure having you on the forum. And we'll hope to listen to you as well in future events. Thank you very much. Join me now. We will move now to the next presentation. I'm just sharing. Okay. Can you see the slides? Okay.
Yes.
Okay,
Yes,
great.
yes.
Well, the second presentation, we are also very pleased to have Professor Akhtar Kalam from Victoria University. The title of his presentation is The Changing Global Energy Environment Applications for the Renewable Energy Development. Professor Akhtar from Victoria University is the Deputy Dean of the Faculty of Health Engineering and Science, the Head of Engineering of the College of Engineering and Science, and the Head of External Engagement. He is also the Chair of the Academic Board of the Engineering Institute of Technology. He's an Associate Editor and Editor-in-Chief for a couple of prestigious journals. His interests include power system analysis, communication control, protection, renewable energy. He has over 500 publications, supervised more than 40 PhD students, and he is a well-known figure when it comes to consultancy for major electrical utilities manufacturers and so on in his field of expertise. It's really a pleasure to have him among us here, and we're looking forward to listen to him. Please join me in welcoming Professor Akhtar. Please, Professor Akhtar, you can proceed.
Okay, can you see my slides, please? Just a minute. Can you see my slide, please?
It's coming.
Yep, yes. Thank you very much.
Can you put it in single or one slide mode? So it's showing the two slides at the same time. Well,
go to the display setting and
go to display setting. Yes.
Okay. Is it still showing that? Is it?
Yes.
Just give me 1 minute. Now is it showing one slide?
Just yes. Go ahead.
Good. Okay. Bismillahir Rahmanir Rahim. Alhamdulillah wa salatu wa salamu ala Rasulullah. And I'll use my traditional greetings. Assalamu alaikum wa rahmatullahi to everyone who are present over there. In particular, I'm grateful to Professor Ali, Sheikh, Professor Derich, and other organizers from KFUPM to invite me to this wonderful forum. Also, would like to welcome our distinguished guests and colleagues in this forum. Before I start, I always like to start with my name. And as many of you Arabs, you might get a bit scared with my name, Akhtar, and you might think Akhtar comes from Khatar. Khatar means dangerous. And if you add alif in front of Khatar, it becomes the most dangerous, and Kalam is stalker. So many Arabs have these problems with my name. and I worked in 2 years in Baghdad. Every time I had a problem with Akhtar Kalam, I was Abu Dakhtar Ali, and all sorts of things was given to me as a connotation. Believe me, I'm not a dangerous talker at all. So with that introduction of my own, today's presentation is looking at the changing global energy environment and to find the implications for the renewable energy development. And just wanted you to understand that we have gone long way from the days when we could see power systems as you see over here. It is no longer that type of power systems that we have. No longer we have this. We have got a completely different scenario today. And if you look at the waves in the electrical industry, in the early 1900s, we had the generators. Then in the 20s and 50s, we had HVAC transmission system. In the 70s, we saw a lot of HVDCs and power electronics coming in. Then we saw combined cycle plant where efficiency went over 60%. Then we talked about wind turbine in the 2012, where now we are looking at wind turbine the size of about 10 to 14 megawatt. But this is the year of digitalization, and we are looking at microgrids. There's been significant changes. No longer energy is coming from generators to the customers. No longer it is a monodirectional energy balance. You will see that you've got a complete smart system where there is bidirectional flow of energy. And the whole transmission system has become very smart, and the distribution system has become extremely smart. Look at the world environment. All of you know that the population is about 7 billion people around the globe. In Australia, our population is small, it's 24 million. 17% of the people do not have electricity. 40% of the population rely on solid fuel, even now, for cooking and heating purpose. And you'll be surprised, majority of the world population has a very low standard of living. What is the future going to be? In the next 10 years, is going to increase by 1 billion people. Most of that will happen in the underdeveloped countries. We anticipate by 2050, the population will be close to 10 billion people. And there will be a huge demand for electricity. And the demand will be anything between 200 to 300% of the present capacity. So the whole process is going from disruption to transformation. Industry is changing. We have got huge amount of disruptive forces. Most of this disruption has been good for consumers. Try and understand that now consumers are no longer consumers. I call them prosumers because they are producers as well as consumers. So I refer to them as prosumers. Then transformation has had an adverse effect on the customer. And if you look carefully, this effect has been a top priority. Naturally, we are looking at competition and innovation. And this is one of the reasons that in Australia, we say that the energy sector is showing the way. A lot of regulatory reform has happened, We have had technology standards. We have got competitive neutrality. We've got ring fencing of monopoly business. And we have got cost-reflective network tariffs. So if we do not manage this transition well, we will lose all the opportunity to transform the industry in a way that will bring the prosumers to us. So let us look at what we had. This is the three directions that has been going on, which has been good for all the prosumers: the technology, the regulation and policy, and competition. Today, our consumers or the prosumers are passive. The grid is still the same. There's still renewable energy. There is still all these energy storage. There is gas system, whatever thermal system is there, right? But the demand has been fluctuating. Now, we have got a completely ubiquitous energy model where this is the demand. But look at the prosumer. The prosumer now has got energy storage. The prosumer has now got distribution generation. The prosumer has got a complete smart control system, and all of us have got digital meters in our switchboard. So the whole ecosystem of the energy is such, which is from the equipment or technology supplier to the consumer. The whole energy industry can be divided into two things: non-renewable and renewable. In the non-renewable, you've got coal, oil, and gas. In my part of the world, we are going to remove all this by 2050. We will not have any coal-fired plant in Australia beyond 2050. That is a plan. At the moment, 78% of our energy comes from thermal plant. More and more people are looking at huge amount of investments in solar, in wind, in biofuels, in hydro, and in other fuel cells or geothermal product. I don't want to talk too much about it because Martin has given a very good thing on the PV system, but you can see the capacity by various countries. In particular, three countries come in mind: US, China, and India. We look at the amount of capacity they're going to be having. So if you're looking at tackling global warming, we heard in the morning a lot of things on global warming. We heard about CO2 emissions, how SABIC and Aramco are trying to reduce their CO2 emissions. From my side, I will tell you that we are looking at demand side, the supply side, and the adaptation. In the demand side, we will be having more and more efficient end user appliances, and the demand of the consumers will be low. We'll be looking at energy saving light bulbs, efficient air conditioners, and freezers. 80% of our projected CO2 reduction is by 2030, and that is to come from demand side efficiency. In the supply side, we are going to be producing energy from clean sources like wind, solar, biofuel, nuclear, etc. I must admit, Australia will not be going for nuclear because we are a nuclear-free country, and we have got legislation in place that we will never be going to nuclear plant. Although we have one experimental plant in Lucas Heights in New South Wales, which is an experimental station, which is a nuclear station. But we will be producing energy efficiently. We will be reducing emission, and we will be going for reduction in our deforestation. So some of the things that we are doing, we are strengthening our flood defenses so that we can adapt to the climate change challenges that we are facing. What is contributing to the CO2 and the various source? This is the transportation sector. So you can see 1/3 is taken by the transportation sector and 1/3 by the domestic residential sector. Now, my question, is there an alternative? If there is, let us see what is there. And then my question is, why do we want to go to renewables? Because you do not deplete your natural resources. Remember, the public wants renewable because everyone is concerned about global warming. It is hitting public conscious, political conscious, you name it, everyone is talking about global warming. We have to look at effective method that we can reduce our CO2 emission without sacrificing our lifestyle. We have to guarantee energy security, and we have to have legislation that will make renewables more attractive. Unless and until the government does not provide incentive, renewables will never take off. So the key areas in renewable is the solar power, which is PV and solar thermal, the wind power, onshore and offshore, the biofuels. The first generation were the agri crops. The second generation are cellulosic feedstock, and algae is the third generation. And hydropower. Unfortunately, in Australia, we do not have too much of hydropower, but we are using it for pump storage. One state in Tasmania has got substantial amount of hydropower. We have the Snowy Mountain, Snowy River scheme, which is our River Murray, which is going from Queensland all the way down to South Australia. That is the major single river that we have. Solar energy can be captured by PVs, by thermal panels for heating purposes. Okay, many will say that this is an expensive method of generating electricity compared to conventional sources. This was the original thinking. We were talking at that time of producing energy between 2 to 4 cents a unit from thermal power plant. And we heard in the morning Dr. Ahmed mention that he's in Saudi, you're looking at 2 cents per unit, and in United Arab Emirates, you're looking at 1.4 cents a unit. So therefore, the renewable is no longer that problem of cost effectiveness. There has been a lot of advances in technology, and we are seeing a lot of solar penetration happening in the world today. What are the pros? Solar is the most available source of energy, widely available, more than wind and hydro. You can have huge amount of potential in a decentralized power generation. This technology is very attractive because you can store energy, you can scale up and down, you can increase the demand, which is driving down the cost, so you can get grid parity. Some people might say this is the most expensive form of energy, but as I told you, this is not at all an issue. You heard Professor Martin Green talking about $1 per watt was the assumption, and now they're thinking in 10 cents per watt for the panel manufacturer. People will say there's a huge amount of capital investment. There is always a debate that it cannot supply the base load power purely because of the intermittency and because we are dependent on solar sun power. And because of that fluctuating nature, there is a stress on the grid. And the most important thing, you cannot store this energy. If you have got excessive energy, unless and until you look at batteries, fuel cells, etc., you will not be able to store this energy. So if you look at the PV market, and I don't want to go too much into it because Professor Green has mentioned that is going to exploit, that is going to increase. You will see that by even now, we have had a complete increase. We have got about 65.3% increase, out of which policy driven wise was about 2/3, and 1/3 it was because of the economics. And the main countries which has done all these things are these few countries that you see in my list. Okay, PV costs are going down. You can see that I have gone up to $2 per watt. Professor Green showed $1 per watt, and he said that this most probably is going to be 10 cents per watt. So, as you can see, there are so much difference in the prices that there is no more any issue with people taking up PV panels. I know in Melbourne, in Victoria, in Australia, if you ask and get a approval to put a PV panel, it'll take you about 2 months to get the PV panel on the top of your roof because there is so much queue in there. Wind power. We all know it converts kinetic energy to electrical energy. It's a renewable energy choice in Europe and United States. And that is because of the increased size and higher productivity has enabled wind generation, which has become competitive. And they were talking, when they are talking about this, they are saying this is about 8 to 10 cents per unit. But as I mentioned earlier, when I heard Dr. Ahmed say that in UAE, you're talking about 1.4 cents a unit, in Saudi, you're talking about 2 cents a unit. But there is uncertainty. Because of the unpredictability, you are dependent on the weather. And utilization rate is 25 to 35%. Okay, but there is no doubt about it that the uptake is very much in China, US, Germany in particular. I will show it to you. Germany in particular has been, after the Fukushima disaster, are going for all the wind generation. Now, the advantage compared to solar and hydro, land requirement is small. You can build it offshore. It will fluctuate less than solar, and it was cheaper than solar. The cons. The premium onshore site has become saturated. Intermittency is a big issue. Offshore plants are expensive, not viable to store energy. And one of the things which is a very important thing is noise pollution. I don't know whether you realize this or not, but those wind generation produce a frequency where there is a tendency for children who are living in close proximity to the wind turbine to go deaf. Because we as engineers have never learned to work with those who are in the medical field and others and look at what is the impact of the pollution on our family life. In Australia, you cannot build a wind generating farm if there is a residence in 2-kilometer radius. So beyond 2 kilometers is the only place where you can get permission to build your wind farm. So the projection is to grow. There's no doubt about it. Today we see that if there is a scenario, we will be looking at about 600 gigawatt to 800 gigawatt, depending on what the policies are, whether it's a new one, is it a moderate scenario or the advanced one. But look at that. We are going to go 3 times bigger in the next 30 years. Look at that. We're going to become bigger and bigger. There's huge challenge that is going to come because many of the countries in the world are going to take up wind as a great source of energy for their countries. Biofuels. Not much has been talked about this morning about biofuel. Ethanol is an alcohol distilled from plant material. In the United States, they use corn, sugarcane in Brazil, wheat in Europe, and these are used as gasoline substitute or blend stock. 90% of the global ethanol production and consumption is in US and Brazil. This can be blended in 10% of the gasoline pool without any noticeable impact on vehicle performance. You can see if you go to the gasoline station, I don't know about Saudi Arabia, but in Australia, if you go to a gas station to buy petrol, the ethanol-based one is about 10 cents cheaper than the unleaded petrol that you get. The biodiesel is produced by transformation of animal fat or vegetable oil into a conventional diesel substitute. Feedstock represents more than 80% of the total cost of producing biodiesel, compared with 60% for ethanol. The advantage is it is renewable, less pollution, much less than petroleum-based gasoline and diesel, and it's easier to transition without any infrastructure. The problem is we do not have enough land space to grow crops for biofuel demand. The question is whether producing them requires more energy than they generate. People ask this question. We still are polluting when compared to wind or solar. Then come the classical hydroelectric, and we are doing a lot of work in the hydroelectric because we do not have too much of hydropower, but we are doing that for storage purpose, pumped hydro storage. We're using it so that we can get a better return using hydropower. This is the most mature of all the renewable energy. It's been there for hundreds of years. It is the largest global contributor amongst all the renewable energies. Utilizes established technology from other sector. You can switch on and off immediately, and the cheapest wherever it's available. The problem is that the advantage is that it is cheap. It can provide base load, so I can replace my thermal plant by a hydro plant if I have enough capacity, and I can go for large scale production. The problem is that ecology in dam, that is environmental concern. Because the settlements are impacted, the humanitarian implications are there. There could be seasonal nature of aura in the catchment area, and it depends very much on the season. Capital costs can be very high because you're building this dam, and limited number of potential sites or locations which are available. But if you look at that, the key players are still China, followed by Canada, Brazil, and United States. Those are the 4 or 5 countries which have got enough hydropower and who are using that. So now let us look at the economics, because every one of us are interested in economics. How feasible is that? And let us take the German example. In 2020, they had 35% renewable. Now they are going to the 50% renewable stage. In another 20 to 30 years, they will have 80% CO2 reduction by using this green revolution. If you go to Germany, you will see all these sites. Every house has got PV panel, there are wind turbines, etc. If you look at the renewable energy source in feed versus load in Germany, you see that this is the source which is coming from PV and from wind, and this is the cumulative one. This is PV and this is wind. This is sun plus plus wind is the cumulative one from sun and PV, and that is wind and PV produced about 34 megawatt, where the load was about 51 megawatt on that day, and that was a public holiday. Whereas if you look at on another day where there was very low in feed of renewable, look at that, wind and in feed approximately 150 megawatt, load was about 41 megawatt. So only 0.4% of the load was covered by the renewables at that time. This is how in Ireland they are having integration of all the renewables in that part of the world. Look at other part of Europe. Here they have got in Germany they have got a 600 megawatt line commutated converter. In Sweden they have got another HVDC which is using voltage source converter, and in Australia itself we have got a line commutated converter in our Basslink, which is connecting Tasmania to the rest of the mainland. So these are the submarine cables that we have got in our Australian scenario. We are also using shale gas. This is very common in the United States. This is the natural gas formation which is trapped in shale formation. This has become a very important natural gas in the United States, and this is spreading all over the world. So look at what is happening in the United States. From 2009, most of the thermal plants are being retired and they are being replaced by green power plant. If you look at the transformation in US generation, you will find that gas is exceeding the coal because all the coal plants are being converted into gas. And more coal retirement probable, there will be stress on their nuclear plant. Again, advances in renewable. If you see that the non-renewable energy is only 3.2% growth, whereas the game changer, which is solar, has got about 7.5% growth. If you look at the American demand, typical home is down by 4%, and that is because the lighting, etc., have all been completely revolutionized with CFCs, etc. So you see that there is a stagnation, and you will find many power companies will have difficulty surviving because the demand from consumers, from the generators will become very small. They all become prosumers. They will be utilizing their own energy that they produce.
Professor Akhtar, if I may, Professor Akhtar, you have around
please.
6 more minutes if you don't
mind.
Oh,
I'll finish it, inshallah, inshallah.
Okay, thanks.
Okay, look at the fundamental foundational elements. We have to modernize the grid. We have to look at integrated grid. We have to look at interconnection rules. We have to look at policy and regulation. We have to be careful, or else we will have, with the example that we had with Fukushima when the nuclear disaster took place. And that was a huge accident which was due to tsunami at that time. And severe accident took place where there was loss of cooling, core damage, power due to earthquake, damage due to power services, there was leakage, etc. So you see, in China, this is their load center, and look at that. Now they're replacing that with wind. And this is their beautiful Three Gorges Dam. Those who have not seen it must appreciate the beauty of this dam. This is producing energy to main China. Look at that. They are thinking of sending this energy all the way to Poland through 5,635-kilometer pipeline. In India, the scenario is the same. They have about 60% coal-fired plant. They want to go to the renewable. And they're looking at all sorts of technology. Look at all the technologies that they've got. They're even considering HTSC. Look at the connection between the East and the West, how the pipelines are going through. They're looking at HVDC and interconnection, finding all sorts of advanced metering, outage management system, and the voltage source converters. Then in Brazil, that is a typical dam that you have producing electricity, another experience of Brazil. In Africa, a unique design suited to African environment. Look at a typical African village, how they are supplying energy, a typical township where there will be schools, etc., and the lines will be going adjacent to it. And this is how the US city will look like. This is a US city, and I think there will be a cultural difference experience if you see this type of experience that is there. So my question to you is 100% renewable. Is it possible or not? Okay. Is it cost competitive? And my answer is yes. In summary, I have talked about 100% renewable, and I'm telling you it is worth thinking about. The question is not whether it will happen or not. The question is, when will it happen? Is it technically feasible? I tell you with very high confidence, it will happen, and all the technical issues can be resolved. Cost, I have told you that it is manageable, but we have to look at the anticipated gas and carbon cost. Will the market work? The answer is that we will challenge the existing market model, but dramatic market reform is unlikely to be warranted at this time. With that, I've completed my presentation. Jazakallah khairan. I think I've done it in time, Mohammed.
Yes, you did. Thank you very much, Professor Akhtar. Really appreciate
Ahlan wa
it.
sahlan, ahlan, ahlan.
Especially this dancing electricity pole at the end.
Yeah, that is to impress you, Dr. Mohammed.
By the way, if you look at that, I know that it is an image processing problem, which is my expertise.
I know, that's why I put it there. I knew that you are going to tell me that. Last time when we talked to each other, you said you are DSP and image processing person. I thought this is a typical classical Mohammed Darichi type of transmission line.
Thank you very much. Thanks, Professor,
Ahlan.
for this excellent overview. We really appreciate it. We have a few quick questions we want your kind of feedback on. One question here is about wind. You mentioned the comment that energy storage for wind type of source is not viable. Can you comment on that?
Okay, what I was trying to say is that when we are talking about, because someone had asked this question also in one of the 34 questions which is there that I'd seen, someone had asked this question about the Australia's storage capacity. We have built a 100 megawatt Tesla battery, and I think we are going to go to the Tesla battery. The next one we are building is 150 megawatt. Both of them will be the world's largest storage facilities that we are going to have. And with renewable, if you do not have the storage capacity, you're going to have problems. We did have problems in 2016 with in South Australia, which has got 40% renewable energy, when the whole state was blacked out because of the voltage tsunami that hit that place, and there was no power coming. There are two states which are connecting to South Australia. Victoria is one of them. Queensland is the other one. And from Victoria, we had 500 kV going to South Australia, 330 kV was going from Queensland. There was a voltage tsunami, and there was a frequency dip, and that went down below 49.2 hertz. And we found that there was no way on the earth that we could save. So the first thing we did from Victoria, we switched off South Australia completely, and the whole of South Australia went to darkness, and it was in darkness for 3 days. It's a huge loss to the industry and to the renewable energy. That's why Elon Musk, when he came up with the idea of producing 100 megawatts in 3 months, he produced this plant in 3 months, 90 days, and he's going to produce in 150 megawatt in Victoria in 90 days again. So what I'm trying to say is that storage with the wind is a capacity which is possible.
Thanks, Professor Akhtar.
Or else you're going to have blackouts. You're going to have blackouts. Be very careful.
Thanks. Another question here is with regards to biofuels. What do you think, or what's your opinion on the food to energy nexus?
Look, in a country like Australia, which is the food bowl of this part of the world, we are supplying to China, to Japan, to the whole of Southeast Asia, and we have abundance of agriculture product. Now, you must understand, Australia is just like Saudi Arabia. There's no difference between Australia and Saudi Arabia. The whole of Australia is worse than Sahara Desert, except the coastal part. Worse than Sahara Desert, remember that. Okay? So you have to be very, very careful about that thing. People do not understand, but that agriculture is one of the most important export market that we have. And we have got a lot of food waste. Can we utilize the food waste to produce energy? The answer is yes. The answer is yes. We have got a lot of animals. We export meat product to Saudi Arabia, whether it is in the form of lamb, it is the form of goat, whether it's form of cow, whatever it is, we sell it. As a matter of fact, in Saudi, I found that the Australian meat is the cheapest in the Saudi market, and we are doing that. But then they cost us a lot of energy. So we have to be careful. Can we utilize the waste? And that is what we are doing. We have done that with pig farm. We have done that with chook farm. We have done that with cow farm. It is a lot easier to collect in those portions than in cow and all, because cows stay separately. Yes, it is possible, but it is costly.
Okay, thanks. Maybe one last question, if you don't mind, Professor Akhtar. Someone mentioned about the geothermal that was not kind of mentioned in your presentation, as well as tidal power as a game changer. What's your
I agree with that. That is a wonderful question. Thank you very much, whoever asked that question. Thank you very much for that lovely question. I had it, Mohammed. I removed it because my slides went more than 66 slides and I could not finish in 45 minutes. Yes, I agree. Geothermal is an alternative to baseload coal-fired plant. Listen to me very carefully. Geothermal is a replacement to a coal-fired plant. That is the only thing which I can guarantee you will give you base load. The problem is that to find the good source of geothermal source, that is the hardest bit. In New Zealand, we have got a lot of volcanic rocks, etc., where you can do it. In Australia, in the border between South Australia and Victoria, in Portland side, we have got community swimming pool, etc., that we're extracting from the geothermal energy. In Sunbury side, about 20 kilometers north of Melbourne, where I live, they have got geothermal site where they're extracting it for heating purposes. However, in countries like Australia, which is a huge country, geothermal sites are very limited. New Zealand has got an excellent site and they can replace it with so geothermal is definitely an alternative. Ocean is an interesting one. Someone mentioned ocean and tidal. That is an interesting one. And in a country like Australia, we are surrounded by water all around us. You know that. We are surrounded by water all around us. The problem is that Australians are sports-loving people, and half the time they are submerged in water. And you will find them in swimming and doing this and doing that. They would not like to see any of those dikes near the plant. In Western Australia, in Fremantle, we are producing ocean thermal, but to become it long-term to supply base load will be difficult because the population will not accept it. There will be a lot of negative publicity from the population. I rest my case.
Thanks, Professor Akhtar. And actually, nice comment, because I know that Aussies, they can sacrifice everything except surfing.
I tell you, you name it. I've got this problem with my own family members, so don't start that.
Thanks very much, Professor Akhtar. Really appreciated. Okay. Excellent presentation. And we look forward to listening to you in future event, inshallah. So now, if we can move to the next presentation, the last but not least presentation in this session. Let me just share the title. So here, so this is our third presentation for this session. And we are really fortunate to have Professor Fausto from Spain to speak to us. Professor Fausto, are you with us?
Yes, I'm here.
Okay, great. Well, it's really a pleasure. And actually, the interesting thing is this. Professor Fausto is kind of marrying two areas which are more and more being connected more and more, especially one area which is really dear to my heart, which is the issue of machine learning and AI. And bringing that on board to the sector of renewable energy is an extremely important issue. And we look forward to listen to him. Professor Fausto works with the UCLM in Spain. He is also an honorary senior research fellow at Birmingham University in UK. He received many awards, including the Runner Prize for Management Science and Engineering, nominated prize, an advanced prize in 2018, the first International Business Idea Prize, the runner-up in 2015, the Advancement Award, and so on. He has a humongous list of awards and achievements. He has published more than 150 papers. He received a number of best paper awards. He is the editor of about 25 books, and he is the editor of 5 international journals. His research interests include AI, maintenance, management, renewable energy, transport, advanced analytics, and data science. We really are very fortunate to have him among us here, and we are looking forward to listen to him. Please, Professor Fausto, the floor is yours.
Thank you very much. I don't know if I need to share my slide with you or
yes,
you share the slide.
Yeah, go ahead.
Go ahead. One moment, please.
Can you share it okay?
Just 1 second, please, because I have, yes. Okay, can you see now the slides?
Yes, we do. Go ahead, please.
Okay, thank you. Can you hear me?
Yes, we can hear you very well.
Very good. Thank you very much. So, thank you very much. First of all, I would like to say thank you very much to the King Fahd University of Petroleum and Minerals for this invitation, this consideration with me, and also to the chair of the session, it's Ali Al-Saiki, and of course Samad Ahmed for managing all the staffs until this moment, and especially thank you to you, Mohamed Derich, for your consideration and everything. I'm very happy to be the last one this session because now with the great professors Martin and Akhtar. They introduced very well the importance of the renewable energy nowadays. Now I will introduce another concept on that is artificial intelligence and the importance of artificial intelligence in renewable energy. Professor Martin and Professor Akhtar show the importance of the smart system. And we are talking always about artificial intelligence, smart, and all of these concepts, but the presentation today will be in order to show that perhaps we don't have clear enough this concept, because we are talking about that, but maybe we don't have clear enough the concept. This is the overview of the slide of the presentation today. I will introduce some objectives, but not too much, because I repeat Professor Martin and Akhtar, they introduced the importance of renewable energy nowadays, how it is rising, and the importance in the future. So just a few lines about that. I will introduce to my group, my research group, what we are doing according to that. And then I will begin to talk about the importance of artificial intelligence and renewable energy. I will finish talking about wind energy, because today, this morning, we have been talking about many other sources, and I will finish with that. The objective today is here in this slide. Do we have clear enough what is artificial intelligence? Because when we are talking about that, what is that? No, everyone is talking, everyone is writing papers, books, and talking in speaks, etc. But do we have a clear enough what's that? And if we have clear enough what is this concept, where we get this concept? No? Is there any international consensus about artificial intelligence? What is the way of the artificial intelligence, or to the artificial intelligence? Because now we are in the middle of the revolution of this concept, no? And I think that everyone knows that. And what is everyone doing? When I'm talking about everyone, I'm talking about the general politics in the country, and most powerful countries, talking from the economic point of view. And then I will finish talking about artificial intelligence and energy, and what is the current scenario, almost from the scientific point of view, because we know that the scientific point of view is opening the door to the industry, no? So it's the beginning. What is Ingenio? Ingenio is a research group that is located in Spain at the University of Castilla-La Mancha. This is in the center of Spain, and Spain is located in the south of Europe. We have different areas, and the main area is the research group, but now the group is rising, and then we are generating and creating new area just for teaching, located in other universities, or in focusing other topics. The introduction, I will begin to talk about A for People. This is artificial intelligence for people. This is the first multi-stakeholder forum, bringing together all actors interested in shaping the social impact of new application of artificial intelligence. And this is located in focus in Europe. The mission, it was created in 2018 and was launched by the European Parliament. Is as a first multi-stakeholder forum, bringing together all the actors interested in this shaping social impact of new application of artificial intelligence, including the European Parliament, civil society, organizations, industry, and the media. 6 months later, the European Commission established the high-level expert group where I am member of this high-level expert group on artificial intelligence, in which many scientific members of A4 people were engaged. With a 3-year roadmap, we are now in the second one. The goal of the A4 people is to create a common public space for laying out the funding principles, policy and practice, and which to build a good artificial intelligence society. The A4 people is divided in different sectors: automotive, banking, and finance, etc. No, and working in energy. This is they call it 7K requirements for the trustworthy artificial intelligence. The first year, the A4 people was focused only in the ethic of artificial intelligence. And this is in order to create the base and then to show to the parliament, and then the parliament to begin to work in some laws, because there is no liability nowadays regarding to artificial intelligence. And this is very important, because if we see the previous slide, sorry, we have very important case industry here. Today we are talking about energy, but there is another very, very important that is using, and this base or is developing this industry based on artificial intelligence. But if we see, for example, there is no a clear liability on that. There is no law, there is no standards, and this is very dangerous, because if we depend of this technology, if we depend of this advance, the first is to create all of these laws and standards in order to look for the clients, no, the society in general, because this is the most important, no, more than the industry. Here we can see the general scenario for the main economic countries in the world: China, US, Russia, Japan, Europe, sorry. And this is the different politics according to the artificial intelligence on that. So we can see here that is recently, and this is only politics, this is only ideas, this is not only something specific, okay? They are beginning to work in a roadmap, usually for 4 or 5 years. So they are now working on that. Not only these countries, also the rest of the countries, or some of the countries in the worldwide, because everyone is beginning. And when you read about that, they always mention that they want to be the first in order to create that. So the first conclusion is that now we are in the middle of the way. They are working on that. We know that from the research point of view, there is a lot of, I will talk later about that. There's a lot of research, there's a lot of advance in artificial intelligence, but not from the society point of view. The first question is what is related to the ethic. This is very important. Then liability, law, and for that we need to have the standards, etc. And they, in general, in the world, they are working on that. Okay, so we are talking about artificial intelligence, but what does it mean, artificial intelligence? From, if we see, for example, from the European Parliament, they define the artificial intelligence as refers to the system to display intelligent behavior by analyzing the environment and taking actions with some degree of autonomy to achieve specific goals. No? Artificial intelligence-based systems can be purely software-based, acting in the virtual world, example, voice assistant, image analysis software, search engine, speak and face recognition system, or artificial intelligence can be embedded in hardware device. For example, advanced robots, autonomous cars, drones, or Internet of Things application. So here the main conclusion is that artificial intelligence is not only software, it's also hardware. Okay. You can see here in this slide another definitions. For example, the International Committee for Information Technology Standards, the ISO, the Office of the President of Russian Federation, the Japan. So we have different definitions in the worldwide for the same word, artificial intelligence. What is the conclusion? There is no consensus at the moment. They are talking always something similar from one place to another place, but there is no international consensus about what does it mean artificial intelligence. I will talk and I will have the reference from Europe. I'm here in Europe, and so I need to be focused on that. There is no another reason for that. If I work in Japan, maybe I take the definition in Japan or in Arabia Saudi or something like that. No, in my case, is I am in Europe, so I will take this definition. No? So according to that, so I have a reference. What does it mean, artificial intelligence? So I can continue talking about that. But we can see here that for other countries, the meaning is almost the same, but not the same. This is very important. The industry, in general, they need to have reference when they are talking about artificial intelligence. For example, we sign a contract, a very important contract with a lot of money. What do we have as reference for this contract? We need to have laws. We need to have standards. Okay. Here, for example, we have one of the most important standards, the ISO. Okay. You see here in this slide, there are standards ongoing. There is no standard at the moment, so we cannot find this standard. Here in this standard, for example, we have the definition for them for artificial intelligence. This is very important because for the contract, we need to have clear enough what does it mean in order to sign that. And there is another standard ongoing also about artificial intelligence. You have you can see here in this slide some of them. Okay, this is the ISO, but here in this conference, they are focused in IEEE, and they are also working on that, and they are also different projects according to the standards for artificial intelligence. Okay, so it is not clear enough at the moment from the IEEE what does it mean artificial intelligence. They are working on that, and this is very important in order to have that. According to these standards, we know that there is many standards around the worldwide, but usually when they develop any standard, they have as reference most of these standards, and then just they copy and paste, and sometimes they translate this standard and they adopt this standard for the countries and their economy. Artificial intelligence, I think that we have a clear enough that we don't have clear enough what does it mean, and they are going on and working on that. And now I will relate it artificial intelligence and energy. We can see here the evolution of the artificial intelligence and energy publication from 1970 to 2019. No, I didn't consider 20 because you know that the many paper ongoing, and if we finish this year, the numbers that we can get, there's no, we cannot trust that because some of this paper will appear in 2021. What is the main conclusion from this slide? Is the exponential curve that we have according to this research. So the importance of artificial intelligence on and energy, okay, is very important from the research point of view. Remember, research is always firstly than this, the industry. So after that, you will apply that to the industry. So the industry is coming later. So it's very important for the future, the artificial intelligence in energy. Okay. Here we can see that there is some years that maybe you can think that is decreasing the numbers of publication. Don't trust that, because the publication have some inertials. So maybe you submit a paper today, and then maybe the paper is accepted in 1-2 years, okay, or 3 years sometimes, okay, because you submit to one journal, it's rejected, then you can do some modification, then you submit again, etc. So there's some inertials. So this is the reason that sometimes some years decrease the number of publications. So you need to see the general trend of the curve, no year per year. Here we can see the number of publications per country. This is very important also because we can see what is happening in the worldwide. There's nothing strange in this slide, because most of the publication is coming from United States, China, India, and then some countries from Europe. We need to zoom all together. For example, United Kingdom, Spain, Germany, Italy, France, etc. Can we get any conclusion from this slide? No, because this is the number of publications per country. But you know that we are studying this publication for a long period. Okay, so what is happening in the last years? This is per country, not per people. Okay, and there's many countries that they have a lot of people. For example, India in this case, or China. Okay, here we have the trend per year and per country. Okay, the previous slide we saw that US has most of the papers, publication per in this period. But you see here in this slide, you need to focus the attention to China. China is, from my point of view, the most powerful country in artificial intelligence nowadays, and it will be in the next few years. China and also India. They are doing a lot of advance in artificial intelligence, especially in the last years. If we see from the historic point of view, of course, US is the most important from the worldwide in this topic. What happens if we analyze that per people, per population of the country? The statistics change completely. You see here, US, China, India disappear, the first and the last slides. Now we can see here Luxembourg, Australia, Switzerland, most of the countries from Europe. Okay, and Australia, we can see here also. What is the main reason of the research, the papers and so on, the financial support? This is very important. Any country that they want to push the research on artificial intelligence, thinking in energy, they need to invest on that. It's very important to have the financial support from the government. In other cases, it's very complicated. You see here in this slide, what is the country that is supporting more nowadays? The research, China. China is the country that is having more financial support in order to support this research. You can say me, of course, China has more population than other countries. This is true also. We have seen the importance of artificial intelligence. We can see in energy, especially in the last few years. But what is the main topics that they are researching on artificial intelligence and energy? Here we can see this study where we have the energy efficiency, energy utilizations, sensors network, etc. But also, we can see here, for example, renewable energy in this study, solar, wind, etc. They are also including, in this study. And when we are talking about energy efficient, it's in general, but it's also in considering renewable energy. Okay. What are the most important topic per country? Also, we can see here that most of the countries have the same interest in the same areas. This is the main conclusion. But another important conclusion here from this slide when we talk about humans. Okay, we can see here that the country that is researching more about human or is more interesting on that is US. And here, for example, India and China has a little bit less importance on that, in that topic. The rest of the topics, the main conclusion from the different countries. So there's a general consensus in the worldwide according to the different topics, the same worries for the different countries. What are the main artificial intelligence methods? Here you can see this slide, but from my side, from my point of view, this is very complicated to get a conclusion. But so what is artificial intelligence? When we are talking about artificial intelligence, many people are talking about learning system, machine learning. At the end, I have not clear enough if the people have clear enough what are the machine learning, because sometimes from my side, I feel confused, because at the end, they are working, for example, an artificial neural network, and they call that machine learning. Or when they are talking decision support system, it's like a facility system, for example. It's complicated, no? And then we can see here many optimization algorithms, usually mathematics algorithms, for example, genetic algorithms, SCART, many, on that, particular strands, etc. So it's very complicated. But you see, most of the algorithms, most of the methods are using to apply to very complex and robust problems. This is the main conclusion from my point of view. If we see, for example, what is China thinking about the previous slide, about the algorithms, they are talking about big data intelligence, they are talking about cross-media sensing and computing, hybrid and native intelligence, swarm intelligence, autonomous coordination control, etc. If we go to Russia, for example, they mention about the algorithm simulation of biological decision-making systems, including distributed collective systems, so as a bee swarm or ant hill, autonomous learning, and etc., etc., etc. Now I will begin to talk about sustainability and renewable energy. Here I cannot talk too much because we have two excellent presentations before with Professor Martin and Professor Akhtar, that they were talking about that topic and the importance of that. I will mention now the importance from the European Union in general. More than 25% of the European Union's greenhouse gas emissions is given by the production and use of energy across the economic sector in European Union. The economic grew by more than 61%, and the greenhouse gas emission has been reduced by 23% between 1990 and 2018. This is very important because here we can see that the European Union is, the politics is in order to increase the economic, but to reduce the gas emission. This is very important. Not until that moment, also for the future. This is expected to reduce the greenhouse gas emission by 60% by this year. We will see later. To increase the greenhouse gas emission target for 2030 in Europe to at least 50%, sorry, and towards 50%, 55% green regarding with 1990 levels. So the strategy is very clear from the European Union, is to increase the green transformation, and also to invest in the digitalization of this sector. This is very important. Professor Akhtar was mentioned that in his presentation, but not to any price. We need to guarantee the security, that it must be liability and accessibility for the society. So the society is the most important on that. Remember that the European Union is working on that. There is not clear enough about these issues at the moment. They are working on that. The investment in green energy is rising. For example, here we see that in 2005, we have 88 billion of dollars. This is billions from US point of view. It's not from Europe point of view. And in 2018, it was 332 billions. This is the most important. If there's no money, it's very complicated to work on green energy and this topic. The energy roadmap in 2050 for the European Union, they want to reach 97% of renewable energy. This week, for example, in the news, the politics, they were talking now about 100%. I don't trust that. But they are beginning to talk about 100%. We are in the middle of a goal of renewable energy revolution. Investment in renewable energy has continued to increase each year, largely by developing countries and since 2004. The world has invested 2.9 trillion in green energy sources. Positive development so that the renewable energy transition is possible, but advances so far are uneven across sectors. This is mentioned in Applied Energy Symposiums in 2019. I will focus now in wind energy. Why? Because it's my topic, it's my research topic. There is no another reason about that. There is another green sources. For example, Professor Martin was focused on photovoltaic, and then Akhtar was doing a general view of all of them. Wind energy, we need to look for security, clean and efficient energy. We have seen the importance of that, but not only from the green point of view, also on the society point of view, we need to reduce also the cost of this technology, because this technology need to be competitive in the in the energy market. In Europe, for example, it will create 250,000 new jobs with advanced technological knowledge. It is expected to supply 20% of the total electricity consumption by wind energy. A reduction of offshore of the offshore wind energy, cost of 30% by lower operation and maintenance cost and more productivity. This is very important. Most of the technologies are going now to offshore more than onshore in Europe almost. 50% increase in average ability of offshore wind turbines and increase the capacity factor of 10%. This is very important. So it's very important to work in maintenance of that in order to guarantee, because it will depend on this type of technology or the energy source. We need to guarantee the energy for the society, the country, the industry, etc. What is expected for the maintenance in 2025? A growth of annual trend of 11% to reach, in this case, $28 billion by 2025. From my point of view, it will be more than that. We have wind energy. We have seen from economic point of view what does it mean, the importance for this industry. Not just now, not what happened. We have seen what is the importance for the future. But this type of technology is in the middle of nowhere, landscapes, sea, etc. So we need to monitoring what is happening over there. We cannot have people in this type of industry inside, okay? Inside. So we need to have different condition monitoring systems, sensors, etc. This is generating a lot of data, a lot of information, okay? In 2018, we had 33 zettabytes of information in this industry. In 2025, it's expected 125 zettabytes. This is very important because we need to manage all of this data, not only to save, also for analytics point of view. This is the importance of the research. And we have seen previously the importance of artificial intelligence of that, because artificial intelligence can work in complex and robust problems. We can see here the importance of that because we need to process a lot of data in this type of industry. Here is based in two technologies, a condition monitoring system and the SCADA system that we have in wind turbines. The importance of that, is talking about terabytes per day, is 4 times bigger than Twitter in the world. Here we have another data with direct digital transformation investment spending of 5.9 trillion over the years from 2018 to 2021. This topic continues to be central area of business leadership thinking. The major transformation trends we expect to see over the next 5 years. So we are in the middle now. This is rising exponential. This is very important for the new generation to see that. And from the academic point of view, because we need to research on that. We need to provide solutions for the industry and the society in order to manage all of this information, all of this data, okay? Here we have another conclusions from this conference. Here we have some examples from different of the main companies in the worldwide: General Electric, Vestas, EDP, Siemens, for example. From General Electric, they are monitoring more than 150,000 assets, 1,000 signals of sensors per asset, record data every seconds, more than 3,000 wind turbines records, more than 1,000 parameters for wind turbines. If we go to Vestas, monitoring also 3,000 wind turbines, messy numbers. We can see here the complex of this industry, of this technology, and the importance, because when I have been in different conferences and talking with the main people of this type of industry, and I talk with them, and I ask about what is the main worry for them, they are always talking about how to manage all of this information, all of this data. But they are not worried at the moment about analytics. So we need to think that the future is going in analytics. Okay?
So
Finish with the conclusion. I don't know if you were.
that's okay. Go ahead, take your time.
I read your mind now. I applied analytics.
You see, you're speaking about you are using AI now.
But in my case, very short. My mind is very short. So, conclusion: there is no any consensus about the artificial intelligence definition. Artificial intelligence must be developed according to the ethics and the ability. This is very important. Not to do the artificial intelligence because we need that and we need to run. No, slowly with the standard, now thinking about the ethics for the society, etc. New standards are ongoing, mainly in ISO and IEEE. The energy management will depend more on artificial intelligence. The energy future is about sustainability and renewable energy. And wind energy will be one of the most used renewable energy in the future. Thank you very much for your attention. And if you have any question, I will be very happy to give you answers. Thank you very much.
Thanks very much. Thanks very much. I just want to go to this. We have one burning question from the previous presentation. If you don't mind, we'll take it, then we'll come to the questions for this presentation. There was one quick question about the impact with grid in the case of 100% renewable share. And Professor Nazir, we are very fortunate to have Professor Nazir with us. Are you with us, Professor Nazir?
Yes, I am.
Please go ahead if you want to comment on this, so we can proceed with the other questions.
I was not having any question.
No. There was something that you mentioned here. You wanted to answer a question about the grid in the case of 100% renewable share. Or was
no? Yeah, I think that's a mistake. Sorry for this. Yeah,
that's okay. That's okay. All right. So we open the floor for any question. Now, maybe I should just start with a question that I had in mind by looking, Professor Fosso, to these different options of renewable energy, clean or otherwise. Where do you see this concept of AI and machine learning can play a more important role over these different types or different categories of renewable energy?
It's a very complex question, because I think that the research community is working on that. There is a very complex problems nowadays. Thanks to the advance of technology, we are getting more information, more data, and this is getting more complex. You see, for example, from the data, we have different rates, not only numbers. We have also image, videos, etc. We need to process all of this information together. We have also external variables, what happened from the economic point of view, the decision makers, because at the end it depends on the people that they need to have decisions, the competitors, the environments, the prediction of the weather, what is many informations, and we need to put all together. What if we have more informations? We have a better problem in order to get this conclusion. This is where the artificial intelligence is getting more importance of that, because there is no other way to solve this type of problems. This is rising nowadays.
Okay, thanks. We have one question on board here. How accurately can we predict the wind speed over the span of 1 to 24 hours ahead?
Very good question, because now there is a competition, no, for the researcher point of view, because when you work in any research and you develop any algorithms, you talk about the accuracy, and they are talking always about very high accuracy, because, you know, when you have the data, you work with the algorithms and once again until you get a good accuracy that is more than 95%, 98%, okay? But, you know, this is when they are working on that, you know, from the research. And the accuracy is very, very important from one day to another day. No? But the problem is when we have a longer period. So the accuracy nowadays is rising very high. Rising. It's a very high level. We are talking very high level, like between 95, 98%. It's very, very easy to find that. And most of the algorithms, when they try to use that, they order this accuracy more or less.
Well, Professor Fosso, just to follow up on this, I mean, assume I take certain area, not a huge area, but a small area where I have all of the history in terms of parameters with respect to wind, temperature, solar, etc. Can we formulate the problem as an optimization problem where the output from that optimization problem says that, look, for this specific region, under these certain conditions and so on, your best bet is wind? I mean, has there been any work on this?
In my case, no. No. From the mathematical point of view and from the research point of view, you can do that. But
has there been some work?
Yes, but we need to think, and this is from the research point of view, and there is different studies on that, okay? But from the economic point of view, from the industry point of view, it's different, because, you know, why do you have an industry? Because you have a financial support. Where is coming the financial support? The financial support is coming from different funds, public funds. And sometimes the funds is looking for some interests, no? Some politics. And sometimes the politics is going, for example, in Europe, they are looking in Brussels, because according to the support, the economic support that is coming from Brussels, they invest more in wind turbines or solar energy or onshore wind turbines or offshore wind turbines, etc. So then we need to think that the solution is coming from the technical point of view, from the research point of view. That is what we are doing in the academy, to get complex problems related to different constraints and to apply some algorithms to solve that. But also, we need to see that the society and the reality is different, because they have also economic interest that is the main reason in order to do the investment, no, on that. It's the same, for example, to your country, that the government said now, you have a financial support in order to develop wind turbines in offshore, for example. So the industry will be working on that, you know?
Okay, thanks, Professor. So one last quick question. Here it says we are able to enhance the electricity production with several technologies using data analytics. Can we also enhance electricity consumption at the end user level through data analytics? How can we gather the data if the answer is yes?
Yes, thank you. This is a very interesting question, because nowadays, for example, you can see, for example, in my presentation that I was mentioning what are the main topics that they are working nowadays in the worldwide, and I mentioned the efficient, for example, the utilization of the energy, etc. There is many small consumers nowadays in related to renewable energy that they are developing, especially photovoltaic energy in house. And there is small companies that they are developing this industry, this technology, sorry. Also, there is a small company, medium company, sorry, that they are beginning to work on wind turbine, wind energy. So there's many consumers, different consumers in the market, and you need to put all together. But also you can get a lot of information from them, and then this is very complex problems that there are many researchers that they are working on that in order to solve that. And the smart grids that Professor Akhtar was mentioning in his presentation is one of the most hot topic nowadays in the research on this issue.
Thank you. Thanks, Professor Fosso. Thanks for this very interesting point of view with respect to moving to using AI and ML in the energy sector. I think that was really useful for the participants. Thank you again. I just want, sorry?
No, Professor, I would like to mention that I apologize for my presentation because I was very relaxed. I was not running because I just finished my breakfast. I'm beginning my day. But for you, it's different because it's the lunch time, and maybe you were thinking, "Oh, I want to."
Actually, we really enjoyed your presentation.
For everyone for that.
Thank you. Now, actually, the morning was basically from the middle or the European eastwards. Then in the afternoon, which is starting at 1 p.m., will be from Europe going to the west. So I'm showing the slides. I'm not sure whether you can see the slides. Can you see the slides I'm showing?
Yes.
Okay. So we will, basically this session has ended. And I just want to tell you that we have some excellent, outstanding presentations coming with some new stuff. Frankly, I've not heard about it until I started reading about the solar cells and so on. We have one of, quote unquote, the fathers of the perovskite solar cells. Professor Naziruddin is with us. We are really fortunate to have him. We will have two presentations by professors at KFUPM who are working in this sector. Then we are also very much actually excited to hear how Professor Brahim Dancer from Ontario is linking the coronavirus era to the energy sector. We're looking forward to listen to him. And last but not least, we'll hear from Professor Mike McGehee on reversible metal electrodeposition for Windows. I've seen his work, some very interesting stuff. So we look forward. We'll stop now for about half an hour. We will just take your kind of quick break or quick lunch or quick breakfast, depending on where you are. And we will come back at 1 o'clock. We will start at 1 o'clock as scheduled earlier. I know we are a little bit late, but we will start this third session at 1 p.m. And Professor Ahmed Shamshad will be chairing the session. Once again, I thank all of you for attending these two sessions, especially this one here. I thank all of the presenters and the keynote speakers and those who are in charge of this session. And I will give you a break. I will turn off now the mic and the video for about half an hour, and we'll come back at 1 p.m. Thank you for coming on board. Thanks all distinguished professors, and thank for the participants. Thank you. Bye.
So now it's just one more minute.
1 more minute. Yeah.
Yeah, exactly. Yeah, inshallah, then we'll start.
Okay.